Over 2 millennia ago, Roman engineers constructed aqueduct systems on a scale that still dominates the European landscape today. These conduits transported millions of gallons of water across hostile terrain using gravity alone, requiring no mechanical pumps to maintain the flow. Perspectives of structures like the Aqueduct of Segovia suggest they function as continuous, linear downward slopes, essentially flat bridges angled toward a city. In reality, surveyors had to navigate highly variable terrain, bypassing mountains and crossing multi-kilometer topographical depressions that broke any simple linear path. This is a hydraulic grade line, or HGL. Plotted across a 3D topographical mesh, the HGL maps the mathematical trajectory necessary to sustain fluid movement. The initial downward trajectory demonstrates how engineers regulated flow velocity through precise topographical gradients. Where the terrain drops abruptly, the system transitions to managing intense hydrostatic pressure through gravity-fed inverted siphons. To endure long-term shear stress, the conduits relied on specialized pozzolanic material science. The survival of these structures over 2 millennia relies on a sophisticated coordination of passive thermodynamic and chemical processes. Archaeological evidence of terracotta water pipes and stone basins provides a look into the interior mechanics of passive fluid transport. The system operates in a constant state of tension. Potential energy from gravity pulls the water forward, while the conduit walls create opposing frictional drag. Maintaining equilibrium requires the precise gradients found in Roman blueprints. The downward vector of gravity must be perfectly balanced by the frictional resistance of the walls. If the gradient is too steep, the resulting high velocity causes turbulent flow, which increases shear stress and erodes the stone. Conversely, if the gradient is insufficient, flow velocity drops until particulate matter falls out of suspension, leading to sedimentation and stagnation. Maintaining this balance over dozens of kilometers required rigorous mathematical surveying to ensure the flow remained within these narrow operational parameters. These internal flow calculations also dictated the design of urban infrastructure, as seen in these parallel stone and lead pipes. Gradient control establishes the baseline for the entire network. If the fluid velocity is miscalculated, every downstream component is subject to failure. Engineers eventually encountered valleys too deep and wide for an arched bridge to maintain the calculated gradient. Simply dropping the water down a cliff face would dissipate the kinetic energy required to push the fluid back up the other side. The solution was the gravity-fed inverted siphon. The channel drops sharply down one cliff, crosses the valley floor, and rises to a slightly lower point on the opposing slope. Based on the hydraulic head, the elevation difference between the entry and exit, gravity forces the fluid down and pushes it back up the opposing incline. While effective for crossing terrain, this maneuver generates extreme internal hydrostatic pressure. This pressure scales with the depth of the valley. The high elevation entry points remain at low pressure, while the lowest point of the siphon experiences maximum pressure. At this depth, the water actively exerts force outward, creating a high risk of bursting through the stone or lead walls. Crossing extreme terrain required trading a topographical geometry problem for a volatile hydrostatic pressure problem. Containing that outward pressure without modern steel reinforcement required a specialized structural and chemical approach. At the macroscopic scale, engineers utilized the inverted arch. This cross-section shows the high-pressure conduit resting on a curved inverted arch foundation. The geometry directs burst forces outward and downward into the bedrock. This stress-strain analysis shows the arch spreading localized forces across a massive surface area, utilizing the earth as a compressive brace. However, macroscopic bracing alone is entirely insufficient if the conduit material itself cannot withstand continuous fluid shear stress. The solution to this material erosion was found in the geothermal landscapes of the Italian peninsula. Pozzolanic volcanic ash was the essential chemical ingredient used to create resilient conduits. When these ash particles interact with water, they trigger a chemical reaction that forms a dense, locking crystalline lattice. These pozzolanic structures cure and increase in strength over centuries of water exposure. As microfractures develop, the chemical reaction actively repairs the lattice. Long-term structural integrity was achieved by layering macroscopic load distribution over microscopic chemical resilience. A comprehensive view of the aqueduct system reveals the balance of these invisible forces. For the system to function, it must operate in a state of perfect equilibrium. Flow velocity must be maintained, pressure must be distributed, and the material must self-heal. Failure in any one of these disciplines would result in the collapse of the entire multi-kilometer network. The hydraulic mastery described in historical records is the result of this exact symbiosis. Roman engineers achieved longevity by integrating gravity and geological chemistry into a passive, self-sustaining engine.